The purpose of this video is to describe how Meru's wireless virtualization architecture works. So what I'm going to do in this video is describe a very high-level concept in terms of the overall picture of wireless LAN virtualization, and then set up the problem in terms of what we need to address, or the different dimensions that we need to address in order to provide predictable, high-quality user experience, switch-like user experience, and then zoom in on one specific area and start explaining the problems. Okay. So at a high level, the wireless virtualization architecture is the following. In a typical coverage area, users are walking around with 802.11 enabled devices or Wi-Fi enabled devices. There are different devices with different chipsets, different drivers, different settings. There's over 5,000 combinations of Wi-Fi certified options. And wireless LAN, unlike a cellular network, is inherently a client-centric protocol. The client decides which AP or access point to connect to, client decides when to talk, client decides when to move from access point to access point. In order to provide a predictable network, it is really important, as in a cellular network, to take control away from the client and pull it into the infrastructure. But the key issue is how to do it transparently and in a standards compliant manner. So different vendors have taken different approaches. One approach is try to design away the problem of, or the trade-off between co-channel interference and coverage. So fundamentally the problem is as follows. We need to be able to provide coverage, high quality coverage, in an entire coverage area. And at the same time, we need to make sure that the multiple access points that together provide this coverage do not interfere with each other on the same channel. So Meru's approach to this problem is the following. So assume that you have one large coverage area. So we take multiple access points. Each access point transmits at peak power. And all of these access points live on the same channel, and they expose the abstraction of a single access point. So in other words, even though there are 4 different access points providing coverage, from a client's perspective, a client that's sitting here right in the middle and sees these 4 different access points cannot tell that it's seeing 4 APs. It sees only a single access point. So how do we do that? We make all of these access points essentially behave like one. So from a client's perspective, the coverage really looks as follows. Right? So all of these access points advertise the same virtual port or BSSID with respect to the client. So when the client comes into the network and seeks access to the network, it gets only one virtual port or BSSID that it can respond to. Now all of these access points, of course, on the back end have communication through the switch fabric to a centralized controller. So when a client comes in and asks for a network, in other words, asks to connect to an SSID, each of these access points sends this information back to the controller. The controller decides which is the best access point to serve a client and transparently moves that client to that access point. So for example, if there were a client that were sitting here and it asks for a network, the infrastructure would decide that this access point is going to serve this client. Now, there's a lot of details and nuances behind how this transparent connectivity works, and that's going to be dealt with in a separate video. And the key point there is, regardless of the client chipset or driver or settings, with this architecture, we are able to guarantee that a client is always connected to the access point that is best suited to serve it. And it is not a client's prerogative, it is the infrastructure's prerogative. And notice that at the controller, we have global knowledge. Therefore, on the basis of global optimization, we are able to move a client to the appropriate access point. So that's one aspect of it, which is how we are able to create a simple deployment and how we are able to create a cellular-like deployment where infrastructure guides the client transparently towards the best access point. Now let's get to the second aspect of it, which is how all of these access points coordinate with each other and act in unison. So notice that unlike some of these other architectures where these neighboring access points must be on different channels, because the whole architecture is predicated on putting access points on different channels. We take exactly the opposite view. We want all the access points to be on the same channel so that we can provide one seamless view. So correspondingly, the question we need to answer is, how do all these access points operate without trampling all over each other? In order to address that, we need to address two key sets of problems. And I will subdivide these problems into further subproblems. The first one is co-channel interference mitigation. And the second aspect is maximizing channel reuse. And let me explain each of these in a moment. Reuse. With co-channel interference mitigation, the idea is that we don't want two simultaneous connections that might potentially interfere with each other from happening concurrently, right? For example, in this particular instance, let's assume there are two devices and two access points such that these two communications cannot happen at the same time. The goal is to figure out a way to actually preclude these transmissions from going on simultaneously. That's the first aspect. There's a second aspect, which is channel reuse, wherein while you have access points on the same channel and potentially actually hearing each other, you might still have these two transmissions, this one and this one, that can in fact go on in parallel, even though, by the way, each of these devices might be heard by other devices, right? So even though there is in fact reachability across these access points or these stations, it is possible for these two transmissions to go on at the same time, simply because the link quality is good enough that the noise caused due to this transmission is not adequate in order to preclude this transmission. We need to be able to essentially enable these sorts of simultaneous transmissions, and that's what we mean by channel reuse. Now, of course, there's a very simplistic part of channel reuse, which is if you have one access point here and one very far away, in other words, two APs that don't hear each other at all, of course, they all transmit at the same time. So it's not like we have created one big MAC or one big access point. Each of these access points is a simultaneous transmitter. And through our virtualization architecture, we coordinate to make sure that interfering connections will not happen at the same time, but non-interfering connections will happen at the same time. So here's how we do this. So in terms of co-channel interference mitigation, there are three aspects. The first one is, how do you adapt channel parameters or contention parameters The second is, how do you schedule transmissions uplink and downlink? And the third is, how do you coordinate across access points? In terms of channel reuse, there are two key issues. The first one is, how do you adapt the transmit power and the receive sensitivity? In other words, how do you adapt the characteristics of an individual packet transmission on a link in order to maximize simultaneous transmissions? And the second, how do you leverage some specific capabilities of the Lebanon standard in order to further enhance this? Okay. So in this video, we are going to focus on the first aspect, right, which is co-channel interference mitigation. But note that you need to look at this in the context of the companion video on channel reuse, because this lowers collision, this maximizes simultaneous transmission. And these together are what make virtualization or wireless LAN virtualization work in a very effective manner. So now, in terms of co-channel interference mitigation, we talk about three aspects, right? So the first one is adapting contention parameters. The second one is scheduling transmissions, uplink and downlink. And the third one is coordinating across access points. In order to describe this in a little bit more detail, or to understand this in a little bit more detail, I need to, at least at a high level, present how the standard works. And I'll present it at a high enough level that it's possible for you to understand the key aspects without getting into the real nuances of the standards, because that can get fairly hairy.